Hello and welcome to the solution lecture on the exercise you worked on for multivariate regression. So here you can see the folder that was created after you downloaded the file from the web server and extracted the file. So we click on the our projects file to start our studio, and in here you can see we have an exercise file and a solution file, and we will use the exercise file to work on. So let's go through it from top to bottom. I spoke about the data understanding a bit in the exercise description. So let's start with the packages that we will need. So we will need dplyr, ggplot2, coreplot, and we also might use caret. So let's run this chunk. And this chunk is used for downloading the data. So if you run this for the first time, the file is downloaded from this URL and stored in a subfolder called data. And if you run it a second and third time, it's not downloaded again anymore, because it's checking if the file is existing, and only if it's not existing the file is downloaded. All right, so let's come to the data import. So we can check in the subfolder data. We have now the file called airfoil noise.txt, and we also have it in this value file underline path. So we can directly assign it to an object called airfoil noise, and we can use read table and specify the file path. Okay, so now we have here our object airfoil noise with 1503 observations and 6 variables. Okay, I wanted to save you some typing, so I provided this line 68, which is assigning the column names correctly, because if you take a look, the data itself does not have any column names. So the columns are named V1 to V6. So we correct this by running this chunk, and now we have the right column names, frequency, AUA for angle of attack, and so on. Now we will create a correlation plot for this data to understand which variables are most valuable for predicting the sound pressure level. Here again, we will create a correlation matrix object, which we will call core airfoil, and we will store the result of core and passing here our airfoil noise object. All right, and we call coreplot.mixed from the coreplot package and pass our correlation matrix. And here we can see again our circle diagram on the upper right triangle and the correlation coefficients in the lower left triangle. And the next question is, which two variables correlate most to the target variable? So the target variable is the sound pressure level, which is the last column. By visual inspection you can see that frequency has a high correlation coefficient, but also displacement thickness. You also can see this by reading the last line. But we can also write some code. So we can take our object core airfoil. Let's take a look at it. And in here, the last column is relevant to us. So only the column number 6. And yeah, here you can see the correlation of sound pressure level with itself is 1, so we chose the right column. And what we now want to have is we want to sort it and want to get the two most important ones. So at first we pipe the result, what we can see here right now, to the sort function, and then pipe this overall result to the head function, where we only print out the first two results. So that's it. That's also what we have seen in the graph. Frequency has the highest correlation and suction side displacement thickness is the second one. Now we will create the model. So the task is to create a multivariate linear regression model based on all independent variables. So we create an object called model fit and call a function lm for linear model, where we pass a formula, and the formula is very simply SPL for sound pressure level versus, and we want to have all other variables, so we take the dot operator. And of course we also need to specify some data, and that is airflow noise. Okay, so now we want to create some predictions. We will create a new column within airflow noise and call it SPL pred. And with the predict function, we can create the predictions. At first we need to pass an object, which is our fitted model. And we need to specify some new data, which is also coming from the same object, airflow noise. So now we will perform the model performance check, and we can do it at first in the same way I have shown you in the lab section. So we create a summary object, model summary, where we pass model fit. And now we have access to the values within this object. So within model summary, we have, for example, the adjusted R squared. So that's one way of doing it. We have loaded the caret package, and within this caret package, we have a function called post resample. And this is asking for some predicted values, and these are airflow noise and the column SPL pred, and some observations, and these are stored in airflow noise and the column SPL. So you can see this is another way of doing it. It's providing some more results, so not just the R squared, but also some root mean squared error and MAE, so some other performance measures. So it's up to you which way to choose. The question is, does the model overfit? We will create a visualization to take a look. The plot shows the predicted values versus the actual values, and also some smoothed regression curve. So this is our linear regression curve, what we can see here with the blue line. And actually it's looking quite reasonable. So you have seen we have an R squared of roughly 0.5, so it's not too bad, and our model is doing quite good. So the next task is to create a second model that only takes 3 independent variables into account. So we will create the model fit, and the question is now, which are the 3 different parameters that we should take into account? So let's take a look, because we have a bit earlier found out which the 2 most important features are. So let's just change it shortly to have 3. So frequency, displacement thickness and chord length are the most important variables. So let's just take these. Okay, so let's call it frequency. So model fit freq, displacement and chord, so that we know what is included in this model. And we will create our linear model with the LM function that we by now know quite good. And the formula is now SPL versus frequency plus, and the next parameter is suction side displacement thickness, and the next one is chord length. Okay, and of course we need to specify the data as well. Let's run this. And let's again create some predictions. So let's create a new column, SPL pred, let's call it just SPL pred 2, and we call our predict function, pass here the object, model fit frequency, displacement thickness, chord, and specify the new data with airfoil noise. Let's take the second approach again with the function from Caret. So let's use the function post_resample, where we specified some predicted values, airfoil noise, and here we have SPL pred 2, and we have our observed values, which are in airfoil noise SPL, and click Ctrl Enter to run this. And we can see that our R² is significantly lower than the one that we had before. So the question is, did the model performance increase? Actually, we can say no, the model performance decreased. What you can finally do is just to check that everything is working from top to bottom. Just click on knit, and now the document is created, and we have here regression exercise HTML that was just created right now. You can take a look at it, and great, you made this. This is the final result that you have achieved. So thank you very much, and see you in the next lecture.